everybody, welcome back. As promised a few lessons ago, today we are going to look more deeply into this very special distribution called the sampling distribution. So let's get into it. Here is our overview as usual. We're going to look at some different distributions such as a populations distribution, a samples or the data distribution, and the distribution of interest, the sampling distribution. We will then briefly touch on the central limit theorem and how awesome it is, and then we will talk about standard error and the things that affect standard error. So first, let's look at these different distributions. You're already familiar with both of these. This is the one that we're going to focus on mostly today. So there's a lot of uncertainty in the world in general, and especially in statistics. Statistics is all about trying to quantify some of that uncertainty. We usually have to take a sample from the population when we are trying to estimate a population's parameter, like the mean or the standard deviation. So what are some issues with taking a sample? Well, inherently it is a sample. It is a subset of the population. Even if you sampled really well, it might have some people that were a little high or a little low. So let's say that we have one sample mean that we calculated. If we went out and took another sample with different people, randomly again, would our estimates be exactly the same? Why or why not? Think about this for just a second. So if we went out and took another sample and calculated a mean, would that mean be exactly the same as our first sample? No, most likely not. Maybe, if you got really, really lucky, but most samples, even good ones, will be a little different from one another because of random chance associated with taking a sample. So here are a few different distributions that are plotting different types of data. In the first one, we're treating the data as if it came from the population. You can tell because we're using mu and sigma in our notations. This is like you going and asking every single student at UT how many hours a week they study on average, and then you would plot the data. In the next one, data distribution, this is a one samples distribution of data. This is as if you went out and asked 100 students at UT and then plotted those 100 students. This you can tell is sample data because we're using X bar and S to denote the average and the standard deviation. Now the new one, the distribution of the limelight right now, is this one. This is the sampling distribution. And this is completely theoretical. Yay, theoretical things. But it's incredibly powerful. This one is now a distribution of all the possible statistics of many, many samples. Now that sounds a little weird, esoteric, and very theoretical, but let's keep diving into this. Now, a quick note, a sample is not the same thing as a sampling distribution. One is like a noun and the other one's an adjective in this case. I'm sorry, I apologize on behalf of the entire statistics community. Statisticians are not very good at naming things, so these two things are different. And I will try very hard to stay consistent by using sampling distribution when I am talking about a sampling distribution, which is a distribution of all possible statistics, versus one sample, which is the one sample that you might go out and take. You ask 50 people, that is your one sample. I'm sorry. Really, sincerely, I'm sorry. So here it is, the sampling distribution. The sampling distribution is a theoretical distribution that shows us the distribution of a bunch of sample means. Okay, just keep following, just keep following. So if you took another sample from the population, do you think your statistic will be exactly the same? We've already kind of concluded no, there's random chance involved, so it might be a little different. So how do we know? How do we gauge how much each sample is going to vary from other samples? Another sample that we maybe take later, or the sample that your friend takes versus yours. How much variation is there from sample to sample instead of from person to person? So here is a sampling distribution that I have filled with these theoretical sample means. Remember that these little balls now are no longer people. These are now sample means. So imagine that you and all of your classmates, you went out and you took samples of 100 people and asked how many hours a week they spend studying outside of class. You calculated the average for the samples, your classmates do the same. Now we all come back together and let's say we have 50 averages and we put them all onto a distribution. We want to see how they all look in this sampling distribution together. So let's say that you are X bar 1. This is your sample mean somewhere out here. This is your buddies, and this is your other buddies, and everybody else's. So think back to what we know about variation. In this case, do you think that we want a lot of variation, lots of differences between the 50 calculated sample means, or do we want very little variation? Do we want the data points to be clustered all around one hump in the middle, or do we want them to be far away and spread out from each other? What would it mean if they were very far away from each other? Would that be a good thing or a bad thing? It would be great if the sample means differed very little from each other. If one person calculated an average mean of 2 and somebody else calculated an average mean of 55, there is a lot of variation. We're trying to find the truth. What's the average number of hours each UT student spends a week studying? 2 or 55? Not great. We would hope that most of the calculated means are going to be fairly similar to each other. Again, the most important thing to remember about sampling distribution is that these are sample means and not people anymore. So each one of your calculated means, we plot it here. So a quick note on notation, some of you might be wondering, if we're dealing with a sample, which we're supposed to use X bar and S because it's a sample, why then do we have this mu with the sub X bar thing? Aren't we supposed to only use mu for population data? Wonderful question. And that leads us perfectly into the next concept, the amazing wonders of the central limit theorem. The central limit theorem. Let's explore the wonders of the central limit theorem. The central limit theorem states, as you take more samples, especially large ones, so with really high N, with replacement, that means that people you select, you can put them back in again and use them again, and calculate statistics, like the mean, the distribution of those statistics, that is the sampling distribution, will look like a normal distribution, even if the population data is not normally distributed. And the most important bit is this right here. This is what allows us as statisticians to do good work. You take enough large samples, eventually this mu sub X bar, which is our sampling distribution's average, basically the average of all the possible means, then that average, the sampling distribution average, will equal the true population average, the population parameter we're trying so hard to get to. And now it's considered an unbiased estimate. The central limit theorem is a lot more than just this, but for our intents and purposes, this is what is most important, that with enough large samples, the sampling distribution's mean will equal the true population mean. And this is incredibly helpful and powerful for us. So at this point, some of you might be glazing over and going, central limit theorem, what? I don't know what you're talking about. Okay, give me one more attempt. So imagine that you and all of your peers, you each went out and collected a sample of 100 people and asked them, how many hours a week do you spend working on class stuff outside of class? And each one of you is going to calculate a mean. Now we can take all those means and plot them onto a distribution. And for every one of you who has one that's a little too high, there'll be another one that has the one that's a little too low. Now the average of all those averages is known as that mu sub X bar, this one right here. Now that, remember, with enough samples that each of you all went out and took that were big enough, that average of the averages will equal the truth, the population mean, and that's the thing we care about. That's the thing that we're trying to figure out. Now let's go back to the distribution of all of your sample means. Taken all together, we get a sampling mean, this mu sub X bar, and even a range that would be expected for most of the sample means to fall within. So let's say your sample mean of 21.4 hours was a little low, but still within this realm. Another friend of yours had 23.7, which is really, really close to apparently the truth, which is 24. I've made this up. And another person had one that was slightly higher at 25.6. And then some people had really low and some people had really high. In this made-up example, the population mu, that mean that we're interested in, is 24. And about 95% of all the sample means that each one of you went out and took fall between 21.5 hours and 26.5 hours. Notice how almost all 50 observations are within 21.5 and 26.5. Just like when we were doing the z-scores for height, for example, that most women are going to fall between 2 standard deviations from the mean, it's also true for our sample means. They're going to fall within a certain range. 95% of them will fall within 2 standard deviations. This is going to be immensely helpful when we start doing hypothesis testing. We'll come back to this 95% thing. It's going to be very important in our hypothesis testing later. So remember, the central limit theorem said that if you take large enough samples repeatedly, even if the original population's distribution, that kind of curve, even if it's not normally distributed, the sampling distribution will always be normally distributed with large enough sample sizes and enough of them. Now, what is large enough? Here's our magic number. With a sample size of 30 or greater, the sampling distribution will approach normality. So notice here, these are 3 different distributions. Like this one's even a uniform distribution, and this is with n of 2. This is with n of 5 and n of 30, and notice how the sampling distributions all start to get normal, even though the original distribution was not. Let's see how this could be the case. Let's start with rolling a die. First off, a die has a uniform distribution. Each side, 1 through 6, has equal probability of coming up, a 1 in 6 chance. So the distribution of a die is uniform. Remember that kind of rectangular shape. So let's say that you roll a die 10 times. You get a 1, you get a 6, you get a 4, you get a 3, you get a 5 again. You take the average of all those and you get an average of, let's say, 4. Now do it again. Roll the die 10 more times and take the average. 2.5, 4.5, etc. Now do that 100 times and take the average of all those averages. What will that sampling distribution look like? Something like this. So in case you're wondering, the true mean for rolling a die an infinite number of times is 3.5. So when you roll a die only 10 times, maybe you, by chance, get a whole bunch of 6s or a whole bunch of 1s, so your mean might be a little high or a little low. But here is the sampling distribution for the die. So here's the truth. And let's say that 4 is right here and that 2.5 is here, but still, they will normally distribute because they're going to be fairly close to that 3.5. Now let's move on to sample size and talk about how sample size can affect different things related to distribution, standard error, and our ability to catch the truth. So these are some examples of sampling distributions with different sample sizes. So when sample size is small, there is more variation and the curve is flatter and wider, like up here. As sample size increases, the sample distribution becomes more normally distributed. A smaller n usually results in more variability in our standard error, which is basically the standard deviation for a sampling distribution. When your sample is only an n equals 5, the average you calculate will vary more than it would have if you would have used a larger sample size like n equals 30. Which line, the orange or the black, is probably from a sample with a small n? Black one. It's the black one. Let's pretend that we have 2 sampling distributions. One of the sampling distributions is created from large sample sizes, when the other one has smaller sample sizes. If I reached in and grabbed an estimate for mu, which of these 2 sampling distributions would probably give me an estimate closer to the true mu? Distribution number 1, which is this tall pointy guy here, or distribution number 2, this shorter and fatter distribution. Which one, if I just reached in randomly, would probably give me an estimate closer to the truth? The probability of selecting an estimate of mu within 1 standard error, which is basically like standard deviation for the sampling distribution, that probability is much higher if you are selecting from a sampling distribution based on a sample with a higher n. In other words, distribution 1, each one of these sample means, remember each little ball is 1 sample mean, each one of those had a high number of people in each sample. When in this distribution down here, distribution 2, maybe these samples, each sample only had 5 or 10 people in them. So the bigger the sample size, the greater the probability you'll capture the true population parameter mu, which is what we want. Now it's time to properly address this standard error thing I keep referring to. Standard error is basically the standard deviation, but for a sampling distribution. So let's look at it a little bit more in depth. Once again, I apologize on behalf of the statistics community. Good with numbers, bad at naming things. Now we're dealing with this thing called standard error, which is very similar to standard deviation for populations and samples, but a little different. So let's see how it's different. I've been using the sigma sub x bar in the last few slides. Remember that sigma is the standard deviation, or the average amount people differ from the mean for a population. But now we are dealing with sample means rather than people. So sigma sub x bar is the average amount the sample means differ from the true mean, and it's also called the standard error. It is a measurement of variability for a sampling distribution rather than just one sample, like the standard deviation of a sampling distribution, and it is determined by the standard deviation of the population and the size of the sample that was taken. Remember, we aren't going out and taking hundreds and hundreds of samples. We take one sample with hopefully like 100 people in it, and then we have to make this theoretical sampling distribution. So to calculate standard error, we did this in our z-test, where we take our sigma and divide by square root of n. When mu and sigma are known, meaning they are population data, we can calculate standard error for a given sample by taking the standard deviation of the population and dividing by the square root of the sample size. Again, this is just what we did for our first z-test. But when mu and sigma are unknown and you have to use sample data like x bar and s, we have to estimate the standard error for the sample by taking the standard deviation that you calculated from your sample and dividing it by the square root of your sample size. This guy. The reason that this is an equal sign but looks more like two tildes or little wigglies is because that means it's approximately equal to. So back to our made-up example, the standard error here is 1.25. Based on the 68, 95, 99 rule, we know that 68% of the sample means will be between 22.75 and 25.25 from here to here. 95% of the means will be between 21.5 and 26.5 from here to here, and 99% of the means will be between 20.25 and 27.75 from here all the way out there. Just to reiterate, this is purely theoretical. We'll never actually have access to this. We're pretending right now that we know the truth is 24, and based on our sample size of 50, we would expect 95% of our samples, if you went out and did another one of another 50, 95% of them will fall between 21.5 and 26.5. This again is going to be incredibly helpful for us when we start doing our hypothesis testing. Now let's look at some relationships. What is the relationship between standard error and n? In other words, if n goes up, what happens to standard error, or vice versa? Think about it for a second. As sample size increases, the larger n can now, as the denominator on the bottom, eat up some of that deviation. So as this gets bigger, it eats up all that standard deviation, resulting in a smaller standard error. So as n goes up, standard error goes down, and as n goes down, standard error goes up. So the relationship is inversely related. Now let's look at the relationship between variation and standard error. If your population or your sample had really high variation to begin with, so a really high standard deviation, your standard error will also go up. So in this case, variation and standard error are directly related, meaning that if one goes down, the other goes down. If one goes up, the other goes up. Let's have a little reality check here. In reality, we are not going to take numerous samples because we are very busy and we are poorly funded researchers. And rarely do we actually know mu and sigma. Rather, we use what we know about distributions in the central limit theorem. We take one sample and try to uncover the truth with our one sample, and in some cases, we can use that sample to make inferences about the population. Now, there is still a lot of uncertainty in all of the estimates that we have so far, but using the sampling distribution, we can create intervals around our sample means, these intervals of confidence. So up next, confidence intervals. I'll see you there.